we're looking at constructing tree diagrams and then using these to calculate probabilities of independent events. Now, things to understand and remember is what probability is. It's what you want over the different outcomes, all the different ones available. And then it could be written as a fraction, decimal, or percentage, and all probabilities add up to 1. So key information there. Now, I'm going to show this to you in an example. So I've got 10 cubes in a bag. There are 3 red and 7 blue. A cube is taken at random, colour noted, and then replaced. Then a second cube is taken at random. So what's key to know its probability? It's random. Got random selection here, and then it's replaced. Now it says independent events, so what that means is the event first taking happens has no effect on the second take happening. Dependent is when it's not replaced, but we're doing replacing cubes here, replacing the item. So what a tree diagram is this? You've got your first take is shown here, then you've got your 2 outcomes, red or blue. And then from there, you got your second take. So it could be either this one here or that one there. And this is if you get red on your first go, and that's if you get blue on your first go. And that's the second take. What you have here for each of these, it adds up to 1. So that adds up to 1. This leg and that leg there, if you want to call it that, that adds up to 1. And then the same here, that and that will add up to 1 as well. Okay, the different probabilities, but they're blank at the moment, so we'll get them in a second. So first part of the problem normally is complete the tree diagram, which I have down here, complete the tree diagram. So if you do that for this one, like I said, that's done there. Here, it adds up to 1. So that's 3 over 10, has to add up to 1, that's 7 over 10. And then here, that's 3 over 10, so the bottom part there, 7 over 10. Now, it's a good habit to get into doing this here. So different outcomes. So if we go along this leg, red, red means the outcome there will be red, red. This one here, we've got red, blue. So the outcome of that leg is red, blue. So RB. Here, this one is blue and then red. So we do that. Blue, red, and then down here we got blue, blue. So it's good to make notes like that. And then we calculate the probability. So with this here, we can write them all. It's because you're taking a red, and means multiply, using that and part of the rule. So it's 3 over 10 times 3 over 10. So it's 9 over 100. Here we got red and blue, so 3 over 10 times 7 over 10. So that makes it 21 over 100. Blue and then red, it's now 7 over 10 multiplied by 3 over 10. So again, 21 over 100. And then finally at the bottom, blue, blue, that is 7 over 10 times 7 over 10, which should be 49 over 100. You can check these because all these should add up to 100 or to 1, so it should be 100 over 100. Now, problems you'll get now will be like this. What's the probability of 2 blue cubes? Now, what's nice is with what you've just done, it should be quite easy to solve that. You just go through from your start, 2 blues, blue, and then we want blue again. So it's BV, so it's 49 over 100. So we put there 49 over 100. It's the probability of 2 blues. And then this one here, what's the probability of at least 1 red cube? Now, with that, what it means is you want at least 1 red. So you can look at your different outcomes. Red, red, there's at least 1 red there, it's good. Red, blue, at least 1 red. Blue, red, at least 1 red. Blue, blue, that means there's no red there. So that means you want the total of this, this, and this here to solve it. So you can do it two ways. You can add up these three probabilities, or you can do 1 minus that one there, 49 over 100. So I'm going to do, I'm going to add them all up. So I'm going to do 9 over 100, add 21 over 100, add 21 over 100, and do that. That's 30, 51 over 100. And that's probability of at least one red cube. Okay, now I've got a second question here. I'm going to go over it in a second, but you want a quick look, maybe pause it and give it a go, and then I will go over it. All right, so let's have a look at this question. Peter plays tennis. Probability he wins is 0.6, and he plays 2 matches. So you've got match 1 and match 2, win-loss, and so on. So first thing down there, A, complete the tree diagram. So start doing this. Probability of a win is 0.6. So we can start filling in those 0.6s. So that's a win probability. A win here is 0.6 and a win here is 0.6. So as all probabilities add up to 1, that means the loss for each of these has to be 0.4. So we're using the same probability each time. 0.4, different outcomes we've got going on. So here, this will be a win, win. We got win, loss, loss, win, and loss, loss, lose, lose. And then we calculate the different probabilities. So 0.6 times 0.6, which is 0.36. 0.6 times 0.4, which is 0.24. 0.4 times 0.6, which is 0.24. And then finally 0.4 times 0.4 equals 0.16. And to check it, you can add all these up and it should equal to 1. Now, we want to check here the other parts of the questions now. So what's the probability of 2 wins? So as you've done this hard work of putting the tree diagram together, should be relatively straightforward now. So you want 2 wins. There's 1 win, there's a second win. So win-win, 0.36. You've done the hard work there. Okay, second one, what's the probability of a win and loss? So what we want here is you want a win and a loss in, it doesn't say which order, so it could be any order. So here we got win and a loss. There we got a win and a loss, but it's in the other order. So what we want to do now is take this 0.24 and add it to 0.24. So we do that, 0.24, add 0.24, because we're using that we want win-loss, win-loss, and we got 2, so it's either that combination or that combination, so we add them, and it's 0.48 there. And that is your solution. Realise tree diagrams don't always just have 2 things coming off them. They can have 3. So it could be win, loss, and say, for example, draw. And then here, win, loss, win, loss, draw. Same thing. So it can have 3 options coming off them. So be aware of that as well. And that is using a tree diagram to calculate probabilities of independent events.